In our previous lecture, we were looking at equilibrium applications to dissolving and precipitation processes, which we referred to as KSP, or solubility product equilibrium. And today we're going to focus primarily on equilibriums involving acids and bases. Before we look at the equilibrium involving acids and bases, which deal with what we call weak acids and weak bases, we'll do just a little look, first of all, at a strong acid and some of the calculations that we have done previously relative to such things as hydronium ion, pH, etc., as a little review, and then go on and apply this to weak acid, where we're going to have an equilibrium involved. Mentioned at the end of the last lecture, if we had represented an acid as HA and placing it then with water as a solvent, H2O liquid, the acid donates a proton to the water, forming the hydronium ion and the anion, the negative ion of the acid molecule. Now, in this particular reaction, notice one difference between this and the equations we wrote for dissolving the other day is that I've indicated here only a single arrow. A single arrow implies that the system is not going to reach equilibrium. It is going in only one direction. And so all of the reactant will be converted to product. In other words, the K is so large that we don't ever consider it reaching an equilibrium. So we say that in a strong acid, or also in the reaction of a strong base, that the reaction is 100%. In other words, that it has totally gone to the product side. If it has gone to the product side, 100%, then whatever amount of acid we started with, if we started with 100 molecules of these, for instance, all 100 would have been converted to the hydronium ion. So in other words, we can then make the statement that the hydronium ion concentration for a strong acid now, the hydronium ion concentration is equal to whatever the molarity of the acid itself was, because all of the acid here has been converted to the hydronium ion in the process. So if we started with a mole of this, we would end up with a mole of that. So this is our relationship then. So now we want to apply this idea, dealing with a strong acid, to specifically then a solution of 3.5 times 10 to the minus 3 molar hydrochloric acid, HCl. Remember the strong acids that we've talked about, nitric acid, hydrochloric, sulfuric. These are the strong acids, hydrobromic, hydroiodic, etc. The strong acids, so this relationship holds true. Well, this first part, calculate the hydronium ion concentration, of course, is pretty straightforward because we just said that the hydronium is equal to the molarity of the acid. So we can then say that the hydronium ion concentration, remember brackets means moles per liter, is equal to 3.5 times 10 to the minus 3 molar. So that answers the first question. The second question is, what is the hydroxide ion concentration? This takes us back to chapter 5, where we talked about the equilibrium between hydronium and hydroxide. At that time, we really didn't say equilibrium as much as we just said that in any aqueous solution, that the product of hydronium times hydroxide was always equal to a numeric value of 1 times 10 to the minus 14. So hydronium ion concentration times the hydroxide ion concentration is equal to 1.0 times 10 to the minus 14. Chapter 5, dealing with our first look at acids and bases. Now, this particular relationship here really does come about because of an equilibrium. We didn't call it that at that time, but this is really called Kw, the ionization constant for water, Kw. Of course, we hadn't talked about system equilibrium in that chapter, so we just talked about the numeric relationship between the two. And we see that if we know the hydronium ion and we know the numeric value for the equilibrium constant for that system, we obviously can solve for the hydroxide. So the hydroxide ion concentration then is equal to Kw divided by the hydronium ion concentration. All right, and we can plug in then the two numeric values, 1.0 times 10 to the minus 14 for the top number, and our bottom number from this step right here, 3.5. I'm trying to find one pen that'll write halfway decent here. 3.5 times 10 to the minus third. So if we numerically solve this, then we will have what the hydroxide ion concentration is. So 1 exponential minus 14 divided by 3.5 exponential minus 3, and we have a hydroxide ion concentration then of 2.9 times 10 to the negative 12. So we've now answered the first part, the hydronium ion. We've now answered the second part by using the equilibrium that exists in any water system of an acid or a base, that being this times this is equal to Kw. And now we're ready to go on to the final step of the calculation, which was calculate the pH. We recall pH is equal to minus log of the hydronium ion concentration. Again, you can refer back to chapter 5 if you have any question about pH and calculation. There are many examples of it in chapter 5. And so pH is equal to minus the log of 3.5 times 10 to the negative third. And so if we plug in then 3.5 exponential minus 3 and take the log of that and take the negative, we have a value of pH of 2.46 for a value. Now, not that it is critical, but keeping in mind significant figures, you might say, well, did I not write too many significant figures in the answer? Again, referring back to chapter 5, when we did the math involving pH, we indicated that only the numbers after the decimal point are significant. This is really a power of 10 indicator, and so we only are showing two significant figures. We had to in the number we're working with, so we have shown it in the correct fashion. All right? Any questions on any one of those relationships? These are important relationships relative to dealing with either a strong acid or a weak acid. In this particular case, we've eliminated part of the equilibrium aspect of the acid itself. As we go on now and look at some weak acid equilibrium, we'll see that we have to make some additional calculations. So any questions on any step of that process? All right. Hearing none then, we know that everybody is now an expert at calculating pH from strong acids. Let's look at a new problem here. Calculate the same things, hydronium, hydroxide, and pH, of a 0.57 molar solution of hydroacetic acid, HN3. And the Ka, the equilibrium constant. Now notice that when we talked about dissolving, we talked about Ksp. When we talk about water, we use Kw. When we talk about acids, weak acids, we use Ka. All of these still are the same. They're Keq. They're all equilibrium expressions, equilibrium constants, okay? We just use the little subscripts to, again, identify the fact that we're talking about an acid here, or we're talking about water in the case of Kw, or we're talking about a dissolving process if we use Ksp. They don't mean something different. They just are talking about a specific system. All right. This is a weak acid, however, which means that, in fact, it is going to reach equilibrium. So not 100% of it is dissociated. So the first thing we're going to have to do here is we're going to have to write an acid-base equation for the reaction. So we have HN3 reacts with water, and this time we'll have a double arrow. This will donate a proton to the water, so we're going to end up with H3O plus an N3 minus ion. Now, in this particular case, in order to calculate the hydronium ion here, we somehow have to figure out how much of the acid has reacted. Previously, in the last one with the strong acid, we said 100% reacted, so whatever we started with was what we ended up with. But that's not true for weak acid. We need to find out how much hydronium is formed, how much acid has reacted. We don't know how much. Well, as we did yesterday, then we could say let X equal the moles per liter of acid reacting. Okay? Now, if X equals the moles per liter of acid reacting, then how many, or what will the concentration of the hydronium ion be at equilibrium? X, thank you. Same thing we'd said yesterday. If X represented the number of moles of solid that dissolved, then X also represents the concentration of the anion in solution, or the cation in solution, if they're 1:1 stoichiometric ratio. And we see that 1 acid gives us 1 hydronium, 10 gives us 10, X gives us X. X is the amount that is reacting. So therefore, at equilibrium, the hydronium ion concentration is going to be X. What is the N3 minus ion concentration going to be? X. 1:1 stoichiometric ratio there also. All right? So we have X at equilibrium. Now at equilibrium, how much HN3 do we have? Anyone? All right, let's suppose that I had $1 and I went down to the vending machine and I spent 35 cents on a candy bar. Probably can't get one for 35 cents. We'll find something cheap to buy for 35 cents. How much money do I have left? This is not real high math here, is this? Maybe I've missed something someplace. All right, How much money do I have left? 65. Very good. How did you determine the 65? You subtracted what you had spent from what you had, right? All right. Now, how much difference is it than what we're talking about here? I started with 0.57 moles per liter of acid. How much of it did I use up? X. How much do I have left? Other way around. 0.57 minus X. Okay? We didn't take the 35 cents and subtract the dollar. We took the dollar, which was the amount we started with, and subtracted the amount that we spent. We take the amount of acid that we started with and subtract the amount that we reacted, which was X. And so when we get all done, when this double arrow is established, when we've reached equilibrium, we're going to have 0.57 minus X. That's how much we started with. This is how much reacted. This is how much we have left. Well, you might say, how is that going to help us solve the problem? Well, we know that this is an equilibrium, and therefore we can write an equilibrium expression. K is equal to the concentration of the hydronium ion times the concentration of the N3 minus ion, all divided by the concentration of the HN3. Equilibrium concentrations. We have to have equilibrium reached first. Notice I didn't put water in the bottom term because remember we don't include liquid water in an equilibrium expression. It's a constant in itself. Well, do I have things to put into these values? Well, yes, I do. We just defined it as X for the hydronium, and we defined X for the N3, and we defined 0.57 minus X for the unreacted acid, and in the problem it says that all of this must numerically be equal to 1.5 times 10 to the minus 5. That's the Ka. That's the equilibrium constant for that particular chemical process. And it doesn't make any difference how much we start with. This is an equilibrium value. It's always going to be that numeric value at a particular temperature. And the temperature that we're usually talking about is 25 Celsius degrees. Well, now you see we only have one unknown in there. We just have X, and mathematically we can now solve for X. Well, if we were to carry out this whole process to solve for X, as you might look, we've got X times X, that's X squared. And we've got this number times a number, so we have a number, and we have an X times this number, so we have an X. And if we have a system that looks like this, X squared, X, and a number, what kind of equation are we looking at if we were going to mathematically solve it? What kind of equation has those three factors in it? Quadratic equation. This is a quadratic equation. Mathematically, we have a way to solve a quadratic equation. So we could use that setup, and we could mathematically solve for it. But basically, if we can get by, we're going to use a shortcut method or a simpler method to get an answer. We're going to make an assumption. And hopefully the assumption is correct and we don't need to do the quadratic equation. Not that we can't, but we can find a shorter method which gives us a good approximation. I'm going to look right here. Now, this reaction doesn't go based on the 10 to the minus fifth. It tells us that there's not a whole lot of products when equilibrium is reached. And if there's not a whole lot of products, it means that we didn't use up a whole lot of our acid in the first place. And if that's the case, we might start by making the assumption that the amount that disappeared, the minus X, is sort of insignificant. It's kind of like if we had $1 and we went into a store and we happened to find a 2-cent piece of gum. can't imagine what store, but let's just suppose that there was such a thing. So we spend 2 cents of our 100. Well, you see, that 2 cents minus from subtracted from 100 really gives us very little difference. 98 cents in our pocket or 100 cents in our pocket isn't too much difference. And so that's what we're saying here. We have used up very little of that original acid, and if that is correct, then we can disregard the minus x. Now, we wouldn't say that we could disregard the 35 cents that we spent. I mean, there's quite a difference of having 100 cents in our pocket versus 65 cents in our pocket. That's an appreciable amount. And if it turned out that we were wrong, that this x was fairly large, then of course we would have to go back and solve using a quadratic. But what we're going to do is our first time through, we're merely going to say we think that this is small compared to this. And by small we mean that it should be 10% or less of the number that we're subtracting from. So as long as x is smaller than 0.057, then it's really an insignificant part of our calculation. Well, if we disregard that now, then, and we then go ahead and do an approximate solution, we'll have x times x squared is equal to 1.5 times 10 to the negative 5, times 0.57. Taking this number, multiplying by that now. So we've done just a little algebra rearrangement, and then we could get a numeric value for this. So let's do that quickly. 1.5 exponential minus 5 times 0.57, 8.6 times 10 to the negative 6. Now, this is sort of like what we had that we solved before with the x and x for the two particles when we talked about solubility, an x squared. So how are we going to solve this? We merely take the square root of this side and take the square root of this side, and x then becomes equal to the square root of that. So I now hit the square root, and I have an answer of 2.9 times 10 to the minus 3. Or I can write that, if we want to, as 0.0029. Now, the only reason I'm doing that is so that we can look back here and say, was that really small compared to this number here? And I think you can see that it's certainly much less than 10%. It's even less than 1% of the number. So it's less than losing a penny out of our 100 that we had to start with. And that's an insignificant as far as for quantitative calculations in equilibrium. Yes?
Should we just discount the negative and
The square root, because x could be minus 2.9 times 10 to the minus 3. Yes, we can disregard that because x can't be any smaller than what? X can't be any smaller than 0. I mean, if none of the acid reacted, how much hydronium would we get? 0. We can't have it disappearing. It can't be less than 0. We either have some or none in the system. So yes, the answer to the question was, do we need to concern ourselves with the fact that a square root could give us a negative number as well as a positive value? And the answer is no, we don't need to worry about the negative value because it is not a possible solution to the problem. Mathematically, it's feasible, but reality, it is not. So we don't need to worry about it. Now, we solved for x. And x, if we go back up here, notice that x represented the hydronium ion. And that was our first question in the problem. Calculate the hydronium ion for this acid. So we now can say the hydronium ion concentration is equal to 2.9 times 10 to the minus 3. And I don't know if we've gotten different film or what, but they don't seem to want to hold the ink at all. Now, that's step one. Any questions up to this point? Yes?
How did you figure out, where did you find that you could make the assumption that X was small?
I did it just because I'm lazy and didn't want to do quadratic equations.
So there's no figure that you saw that made you think that it was going to be small?
Well, yes, that's a good question. The question was, what justification might I have used to suspect that X, we're talking about the minus X, that the minus X itself is small? The clue is the value for K. Because remember that if K is much less than 0.1, it means that the reactant side is greatly favored. And the smaller K is, even the further the reactant side is favored. In other words, because K is rather small, 10 to the minus fifth, I don't expect to have a whole lot of product. And because the amount of product is represented by X, then I suspected that as compared to what I started with there, it's rather insignificant. So that was the reasoning behind that. Okay? Now, back to our original problem, which was calculate the hydronium. We've done that. Calculate the hydroxide and calculate the pH were the other two steps. So let's go ahead, keeping in mind our answer there. Let's just go ahead and do pH. pH is equal to minus log then of 2. I don't need the brackets there. Rewrite it. pH is equal to minus log of 2.9 times 10 to the minus 3. And so all we have to do now is take the logarithm of that number that we had, and we have a pH equal to 2.53. Now, this is an acid, so quite obviously as an acid, the pH should be less than 7. Remember, the cutoff point, neutral is 7, acids are pH less than 7, and so our answer makes sense relative to what we know the pH for an acid should be. The final calculation then was to solve for the hydroxide ion concentration, and again we go back to the fact Kw is equal to hydronium times hydroxide, and is always equal to 1.0 times 10 to the minus 14. I say always, I mean always if the temperature is 25 degrees. So we know this one, we want to solve for that one. So hydroxide ion is equal to 1.0 times 10 to the minus 14 divided by 2.9 times 10 to the negative third. And that looks like it should be pretty close to 3 times 10 to the minus 12. Okay? Any questions on any step of that one? All right. Well, let's look at another example here. Calculate the hydroxide ion, hydronium ion, and pH of a 0.61 molar solution of methylamine. Methylamine. Notice that the equilibrium constant this time says Kb. Well, that's a base. So if we see Ka, it means we're talking about an acid system. We're talking about the compound donating a proton. If we're talking about a base, we're talking about a chemical that accepts a proton. All right, the first thing that we need to do is again write a chemical reaction for this overall process. So we have CH3NH2 reacting with water, H2O. Now, this is a base, and seeing that the number is small, obviously it's a weak base. So if it's a base, it's accepting a proton from the water. So we're going to end up with CH3, NH3 plus, and OH minus. Okay? So when we have a base reaction, we end up producing a product side that has hydroxides. When we have an acid reaction, we produce a product side that has hydronium ions. Again, back to looking at Chapter 5 on acid-base solutions. All right. Again, now, here's what we initially started with. So let's look at it this way this time. We'll just write it a little different. We initially had 0.61 moles of this, moles per liter. And we initially had 0 of this and 0 of this. And now we want to know, what do we have at equilibrium? Well, to get to equilibrium, some of this has to react. How much reacts? We don't know. How do we define things we don't know? X. So we're going to say let X equal the moles per liter of base reacting, just like we did before. So once we've made that statement, now when equilibrium has been reached, how much of the methyl ammonium ion would we have formed? X. And how much hydroxide would we have formed? X. And how much of the base, how much of the unreacted base would we have left? 0.61. Again, our dollar in the pocket minus the amount that we spent. Minus X. Now, again, we have only one unknown here, all X's. And our next thing then would be to look at and see if we can come up with a way for solving for the X. And of course, one of the things that we have is a K, an equilibrium expression, Kb. Kb is equal to the concentration of the CH3NH3, didn't give a whole lot of room there, times the hydroxide ion concentration, all divided by the concentration of the CH3NH2. And we know numerically that this is equal to 4.8 times 10 to the negative fourth. That's given in a table. So, plugging in, the concentration at equilibrium for the first ion is X. The concentration of the hydroxide ion at equilibrium is X. The concentration of the unreacted base, 0.61 minus X. And that's all equal to 4.8 times 10 to the negative 4. Didn't leave much room there. All right. Now, once again, notice that we have only one unknown in there, X. We have a numeric value to work from, so we can go ahead and solve it. Once again, if we were going to make a full solution, we would have to do a quadratic equation. But if we can get by without doing a quadratic equation, we'll go ahead and make an approximate solution first, and then we'll come back and make a final calculation. Now, if our approximate answer comes out where this is small relative to this, then of course we're done with that step of the calculation. Yes, we have a question. The question was, is this top one CH3NH3? Yes, it is. It's CH3NH3 with a plus. It's this product. All right? Remember, equilibrium expressions are always products on top divided by reactants on the bottom. Okay. So, solving for this, then X times X gives us X squared. And we're going to have this number times this number. So we're going to have 4.8 times 10 to the negative 4 times 0.61. And we'll figure out what that number is here quickly. So we have 4.8 exponential negative 4 times 0.61. And we end up with an answer of 2.9 times 10 to the negative 4. To get an answer for x, now of course we would take the square root of both sides, and so x is equal to the square root 1.7 times 10 to the negative 2. Or, if we wrote it in decimal form, 0.017. Now the question is that number that we just calculated, 0.17, is that smaller than 10% of this number here? And it is, because 10% of that number would be what? 0.06. And certainly 0.01 is less than that. So therefore, we're justified in disregarding the minus x, and we don't have to do a quadratic. Now, in the problems that you're assigned and in the problems that are worked in the book, the acids that are used and the bases that are used, this minus x term is always going to be insignificant. You will not need to do any quadratic equation solutions. But in the real world, some of these acids are strong enough or the solution is dilute enough that the minus x term can't be disregarded, and so mathematically we would need to solve a quadratic equation. All right, now what is x? Well, if we go back up here, we said that x was the hydroxide ion, and that answers our first question of the problem. So the hydroxide ion is equal to 1.7 times 10 to the minus 2. That was our first question. Now we go back to then asking the question, what is the hydronium ion? And so we have hydronium ion times the hydroxide ion is equal to 1.0 times 10 to the minus 14. All water solutions, this remains a constant. And so hydronium ion is equal to 1.0 times 10 to the minus 14 divided by the hydroxide ion. And that is the ion concentration we solved for using our equilibrium. And that turned out to be 1.7 times 10 to the negative 2. So if we now make our calculation here, we then will have we end up with an answer of 5.8 times 10 to the minus 13. So 5.8 times 10 to the minus 13 is the hydronium ion concentration. So we now have the hydroxide ion concentration calculated from our equilibrium, the hydronium ion calculated from the equilibrium of the water, Kw, and then finally, of course, we can answer the last question, which is pH. pH is equal minus log of 5.8 times 10 to the minus 13, and we have a pH of 12.23. We recall that if pH is greater than 7, the system is a base, and quite obviously 12.23 is greater than 7, so therefore it is a base. Okay? Well, any question on any step of that calculation? The same type, but dealing with a weak base instead of with a weak acid. One of the really valuable relationships involving acids and bases are what we call buffers and buffer solutions. Buffers are important in commercial processes. Buffers are important in our biological processes. And buffers are important in terms of sometimes medicinal processes. So we have a lot of things where buffers become involved. A buffer, or a buffered solution, is one whose pH does not change if we add some strong acid or strong base. pH is a constant for a buffer. Okay? So that is one of their characteristics that's important. A buffer has a constant pH. So whether we add a little acid to it or add a little base to it doesn't affect the pH to any great extent. For instance, our blood is buffered in our body. Our blood is buffered to a pH of about 7.2. I think 7.23. Somebody maybe that's involved in the healthcare area can correct me on that if I'm wrong, but I think it's right around that. It's slightly basic, and it's buffered. So whether I drink something acidic, some soda pop, eat some acidic food, tomatoes, put vinegar and oil on my salad and eat that, whatever the case is, it doesn't affect the pH of the blood. The only thing that affects the pH of the blood usually is something biologically wrong. And as a matter of fact, one of the first tests they do if you're sick is draw a little sample of blood. Well, of course, obviously the first is to check temperature, but if you go a step further, you draw a sample of blood, and one of the first tests on the blood is pH. If that pH is off very far from normal, it indicates that there is a serious biological problem going on, a serious infection, a serious malfunction of an organ, or something of that nature, because the blood should not change its pH. It is buffered. It's buffered with several things. One is hydrogen phosphate and dihydrogen phosphate. It's also buffered with hydrogen carbonate and carbonate. So there's several buffers. It's also buffered with some proteins that are amino acids. All right? So a buffer has a constant pH. Now what composes a buffer? A buffer must contain two things: combination of a weak acid and the conjugate base, that is, the anion of the acid. So if we have something like a weak acid of hydrogen cyanide, cyanic acid, then that would be the weak acid, and Cn minus would be the conjugate base. That's what's left after the proton is donated. Okay? Or a buffer may exist of a weak base and the acid that is formed from that weak base. For instance, in that one, we could use, well, we know that bases turn litmus blue, so we'll make the base blue here. So NH3, ammonia, is a weak base, and NH4 plus is the acid species that we get after it accepts a proton. So a weak base and a conjugate acid. And that then gives us buffers, either combination. Well, let's look at a quantitative relationship relative to a buffer. It asks us to calculate the concentration of the hydronium ion and the pH for a system which is made up of 0.76 molar hypochlorous acid, HClO, and 1.56 molar sodium hypochlorite. The Ka for hypochlorous acid is 3.0 times 10 to the minus 8. Now the first thing we have to do is we have to write an equation for the reaction of a weak acid, which in this case would be the HClO. So HClO reacts with H2O liquid to produce H3O plus ClO minus. Okay, that's just our regular acid reacting with water, donating a proton, forming the hydronium ion and the anion. Now let's ask, first of all, what is the initial condition that we have? Now that we've dumped these things together, what do we initially have in the system? How much acid do we initially have? Okay, 0.76. How much hydronium do we initially have? Zero. Until some of the acid reacts, we don't have any hydronium ion. How much of the ClO minus do we have initially? I heard zero, but that's not correct. We really have, this is a compound, and remember, all 1A and 2A metal compounds are ionic. They're ionic when we dissolve them in there, and so if we have this, we really have then Na plus ions and ClO minus ions in solution. So we really have 1.56 of the ClO ions already present because we dumped them in. Not because they were formed by the acid-base reaction, but because they're in there initially. We dumped these two together to make this solution. Now, we're going to let the acid react with the water. And so we'll say here, let X equal the moles per liter. Maybe it's the pens. Try a different one here. Moles per liter, X equals moles per liter of HClO reacting. All right? Now, if we do that, and then we go back and ask, now what will we have once equilibrium is reached? How much of this will we have after equilibrium has been reached? This is just like the last two we did. Yeah, 0.76 minus X. That's what we started with. We just said let X equal the amount that reacted, so the amount that we're going to have left is 0.76 minus X. How much hydronium ion is going to be formed? X, because that's what we said, and it's a 1-to-1. Now if we got 2 hydroniums per acid, of course it would be 2X. We looked at an example problem with solubility of that type. What is the equilibrium concentration of the hypochlorite ion? Very good. 1.56 plus X, I heard somebody say. Yes, we started with that amount, and if anything reacted up here, we're going to get some additional amount. So we lost some of the acid, but we have added some of the hypochlorite ion. Notice that the only thing now left that is an X all by itself is the hydronium ion. And what was our first question? Calculate the hydronium ion for the system. So if we now put this in an equilibrium expression and solve for X, we will then be able to determine the hydronium ion and convert it to pH. And in our next lecture, we'll go ahead and complete this calculation on the buffer, and we'll talk about some real buffer systems as they apply to our biological systems.